we said, when we have a parametric, we should be able to graph these two and see what it looks like. So let's graph them. This is the easiest way for you guys to see this. So we put our calculator in parametric mode. We're in parametric mode. We come here and we're going to put these two equations in. So we have x is equal to t. As soon as you hit this guy, you're going to get the t. And then the y is negative 2t. Oops, negative 2t. I'm working right. Okay, so we're going to change our window. Our window just has to go from that t value is small. So like we did the other ones, like from negative 5 to positive 5.
I know the t values are
but because this was just a regular graph, if it's an angle, it's going to go from 0 to 360. If it's a regular graph, it's not going to go far. So make your t-step 0.5. Now, when we graph this, we see a line, right? Kind of a wavy looking line. The t-step makes this a little bit sharper looking. We graph this, we represent this line, and we put a little arrow to say, oh, it started up here and it went in this direction. That's orientation. Okay? If you want to play with this a little bit, maybe it helps to get your t-step a little bit better, and it'll make your line a little less wiggly or weird looking. But look, it's going through the 0, 0, isn't it? It's got a positive or negative slope to this line. Negative. Now, what it means is this. At any point, I can find its t value, how long it took to make this, its x and its y. When I want to convert this, I say, okay, we got to get rid of the t. So if we're getting rid of the t, it says solve for t in one equation, and we said in your x equation. So we take this equation, and isn't that already solved for t? I'm just going to reflect this. Isn't t equal to x? Right? Now, it says second. Substitute that into the second equation, my y. So where I have t, I'm going to substitute in my x. So now I have y equals negative 2x. Isn't that a line that goes through what intercept? What's the intercept on this line? 0. There's nothing here. What's my slope? Negative 2. If I made this, wouldn't that be that? Wouldn't it still be that? I just removed the parameter. That's all I removed. The parameter gives us like a third dimension. Rectangular means I'm back to just an x and a y. So don't get confused by the word rectangular equation. That just means give me your normal xy axis. That's all it means. And if I graph this, my thing has to say function, not parameters, not parametrics, because I'm back to an xy thing. That's all that means. Eliminate that parameter. So I can graph this now in my regular y equals, and I can see that's a line that looks exactly like that. The one thing I can't see is like the orientation part, because there's really no orientation if I'm not saying where did this start, where did this end, what time did this go through. Okay, so this is the only steps we're doing for all of these. So let's hit another one. We got this guy. So I'm going to graph this first. I want to see what this looks like. I go to my y equals. And I graph this. 3t minus 1. Oh my goodness. And 2t plus 1. Okay, let's see what this looks like. Oh, this gives me another line. It gives me a line that looks like this. Somewhere like this, right? So somewhere over here, I get a line. Let's just estimate. Somewhere, where's my y-intercept? Somewhere around 2, right? Somewhere close to the 2. Is my slope positive or negative? Positive. My slope is positive. Somewhere around 2. So now, I follow my rule. I take my x, I solve in terms of t. I need to get t equals. I solve in terms of x for t. I need to get this t out of here. So I have to say, get t by itself. So add 1. Right? Because you never see t in your xy's, in your normal y equals. Then it says divide by 3. Yeah, it kind of looks a little bit weird, but that's okay. We've seen, yeah. Just so that we follow this through, I just want to do a few more. So we take this, and we go into your second equation, and now I can eliminate the t. So I say y equals 2 times, God bless you, this mess. Now, if I graph this in my y equals, well, I'm going to put this in my y equals. I have to change my function back to function. I'm going to go to y equals. I'm going to put this guy in, as bad as this looks. 2 times, let's see if I can get this to work, alpha, y equals. I can't get this to work, so I'm just going to put fraction here. I'm going to say x plus 1. Look what happens. I get an x. I'm back in a regular graph. X plus 1 divided by 3. Oops, to multiply. Thank you. This is so annoying. I'm sorry.
So we said on that side of the board.
Yeah, and then the other side, it just keeps bouncing back and forth on me. So now I'm just going to do a zoom 6 and let this graph a normal graph. Oh, isn't that the same exact line?
Exact same line.
Exact same line. So the exact same line. I'm still crossing somewhere around the 2, and I didn't even make it look any better than this. Yesterday we made this look a little bit better. We said, okay, let's multiply this, distribute this. 2x plus 2 over 3 plus 1. So we broke this down and said 2/3 x plus 2 over 3 plus 1. And we added 1 plus 2 over 3. You could add it in your calculator. 1 is the same as 3 over 3. Oh, isn't that real close to 2? 6/3 would be 2, wouldn't it? 2/3 x, positive slope. There's my equation of y equals mx plus c. Okay? Same line. So all we're doing is going back to something that just contains x and y. It's got to graph the exact same way. And this kind of gives us a hint. We've got some kind of parabola here. I think we did this in class yesterday too. This was our classwork. It came up like this, a parabola that was very narrow when we put this in our parametrics. When we converted this, yeah, that is a parabola that's narrow. That's 16, stretches it out. My vertex is still at 0, 0. Looking a little bit better?
Yeah.
It's kind of like a little bit abstract, like where does this t live? This t doesn't really live anywhere. It's actually on your graph card. Tomorrow when we do an application, I guarantee that you see this a little bit better.
I really hope so.
Yes, tomorrow we do the applications. Because right now, you say, what the heck does this t do? I don't really see t doing anything for me.
What are we doing today?
Today we're just doing a few more of these. As a matter of fact, yeah, I thought we would just do a few more of these, and tomorrow we'll do applications. Tomorrow applications, Monday finish up the applications, Tuesday
What's our
little
test?
tests, and then that's
Okay.
it. Little tests on them.
What day is this final?
The finals, then we'll have like 5 days to review.
Is it the 6th?
The 7th and 8th. June.
Can I?
It depends who you talk to. Some people say June 6th and 7th. Some told me 7th and 8th.
Do you know what days those are? Because I might miss.
How did you do it?
Sorry, I might
Wait,
miss that.
our final for this class is when?
Cause we're not gonna be here. We're wrong.
Okay, so you have to get it excused.
No, yeah, it'll be excused.
Alright.
Cause I'm gonna miss that.
Okay, alright, so make sure you check with your administrators and then.
I'll probably be there for Monday and Tuesday.
Then we'll do your test whatever days you're here.
Okay.
So find out for sure what days you're not gonna be there, and then check with whatever test you have that time frame, to make sure that I give you the test and science.
My science is the week before.
I think then English is the same as math.
Yeah, I don't have English final, so.
Wait, English?
You had reading, so they don't give you the No?
Yeah, I took my reading to the anyway.
But I thought they were still getting the final.
Not for 11th grade.
Oh, alright. I thought they were still doing the final, but I could be wrong there. So just find out and check with whatever teachers you have, and then they'll give you the test. We'll do it that way. Alright, so now, we get down here to something that says sine and cosine. This is an angle. This is still t. Whatever the angle is still t. So you're going to solve for this. You can't separate cosine and sine. Now what happens when this thing goes around is this is where time is. Time is like this. Time is traveling around here. Time travels around. You don't see it. That's why it's a little bit abstract to see. But we do get to make an ellipse. We never get to make an ellipse in our functions, do we? We can't make an ellipse in one equation. If we took these two, and for you guys that weren't here, or if it's confusing, let me try on the side. We'll see what happens. I'm going to set my mode back to parametrics. I'm going to leave this in degree. Okay, I just need to see. This was x equals 4 sine 2 theta. I'll just say t. That's your angle. And 2 cosine. Okay, now, before we do this, angles, how many degrees that they circle around? 360. So we're going to set our window to go from 0 to 360. We don't want to set our step too small, because it's going to take a really long time to get there. So maybe we'll go 15 degrees. Remember, this is in degrees. It's working better over here. So now, when I graph this, oh, look at my ellipse. We never were able to graph an ellipse in your y equals mode. So if I want to see where this is coming from again, let me just change this. I'll change it to 12. We'll go a little bit slower. Look where it starts. Starts here, goes all the way around. And then notice it got a little flatter. It didn't like my changing it to 12. So, but I wanted to get orientation. It started here, and time brought it around. That's where your time comes in. But does it look any different? It's still my ellipse. So now our goal is to get back to the ellipse equation, because does that look like an equation of ellipse? No. But this is how we get our time in there, and it actually does graph a whole figure in here. So what we want to do is solve for sine, divide by 4, solve for cosine, divide by 2, and we have one identity that deals with cosine and sine. So it started here and it kind of went around. We plug this in, we square it, plug this in and square it, and isn't that the equation of an ellipse with my center at 0, 0? My longer one, this is my A, it went out 4. My shorter one went up 2, down 2. Isn't that my ellipse?
How did you get rid of the 2 theta?
Oh, well, it got replaced with a T. It got replaced with my T.
The 2 as well?
So just leave the 2 theta there. Any angle there. It could be any angle.
So the 2 just goes away?
Mm-hmm.
Okay.
Yeah, it just becomes, we keep it together. And this should say 2 over here. So once we do that, we replace it with this guy. Because sine squared, it doesn't matter what angle you put in here. I could put 30 and 30. an illegal 1, 60 and 60. So if I send this to 2 theta, it still equals 1. That is a,
So when you solve it, you don't have to divide the 2 out.
no, don't divide the 2 out. That's hooked up to your angle. Okay? So then we had another similar one. We had this guy. We do it the same way. It's going to give us an ellipse whose center is a little off-center, and major axis would be the x-axis. So 2, 2, 1, 1. If you graphed your parametric, you'd get that ellipse. Remember, time is what's running that thing around there. Time is a little, you can't see it, but it's working around there. Tomorrow when we do your applications, we'll see it. Figured I would wait for applications for tomorrow. We'll get this under our belts, try some more of these today, and then tomorrow be ready to take applications. Okay. This good? Again, solve for cosine. This is your variable. You can't separate your angle from your cosine, or your angle from your sine, because really, sine of my angle is what I'm looking for. Cosine of my angle is what I'm looking for. So I can't separate that. So use your cosine squared plus sine squared, and does it matter what order we multiply those? We add those in? Doesn't matter what order we add those in. This is your ellipse. This is commutative property. So what my goal is to get this by itself, and plug it into this formula. And resolve this for me. This has to say this. X minus squared over 4 plus y plus 1 squared over 2 over 4 squared, which is 16, equals 1. I don't know what happened to the final equation, but it wasn't there. So that's got to have your final equation. And we can clearly see that from ellipse. With the center of 4, negative 1, the y is the major, up 4, down 4. The x is the minor. Good? For you guys that weren't here, is it making sense? This we needed. Yeah? Yeah? Talk to me. Something's not making sense. I don't know till you tell me. The equation came out way down here. I don't know why. I don't know why the equation was so far down, but something happened. This guy, this is the only way. We did this in class yesterday. This one makes a hyperbola. If you put this in your calculator, this will make you a hyperbola. And this was in my calculator when we first came in here, when I first opened my calculator. So if you put this in as your parametrics, let's put this in. So 4, I make a secant by saying 1 over cosine. So I make this by saying 1 over cosine. I don't need that one. And I make this by saying 3 tan. And I graph it. Look at that. This one actually put the asymptotes on there. I didn't get the asymptotes yesterday. I don't see how I got the asymptotes today. That's very strange. Oh, you know what? I might have it in my y equal. I might have had, no, I don't, because I erased it. So I get the asymptotes today. But there's your hyperbola. Yeah, nice surprise. So this calculator has extra features when it's not working well. And then the last thing we did was we have a special equation for circles. For circles, notice, this is where your HK is. This is R for radius. So we have to substitute these in. This is the H, this is the K. Get substituted in. We solve again for cosine. We solve again for sine. We use your one identity, and we get the equation of a circle. And we know that it's a circle because these are the same, and both of those coefficients are the same. And a circle is a special kind of ellipse. We can write it as an ellipse, just A and B will be the same. It's special because it's supposed to be one should be greater than the other, but in a circle they're the same. So just multiply through everybody by 16 and get rid of that denominator. And so here your radius, square root of 16 is 4. There's your center, 2, 1. We got our center, we got our radius. We can graph this with your parameters, or we can graph this with just your xy. Questions? And then I'm going to have you guys do the second one. So, I want to know what this is supposed to look like. So I come to my calculator, and I first put this in my calculator. Everybody put this in their parametrics. I think that's what you're not doing, so you have no idea what it's supposed to look like. So put this in. We'll change your window. Hang on, before you hit enter, we'll change your window because the last thing we did was an angle. So the t-squared, does that kind of give it away a little bit? What kind of figure should we get? We should get some kind of parabola, right? Because we know we're turning into that one. So, question. All right, so hit your window. This is terrible. Go. So we'll go like -5 to +5 and see what that gets us. Put your t-step at like 1. Okay, so I see some kind of parabola out there. It's kind of shaky looking. What should I change? T-step. T-step because this is what makes it smoother or not smoother. So maybe it needs to be a little bit slower. Maybe I'll go to 0.5 and see if that helps. T-step is one of those kind of unpredictables. What do I do? Oh, it's a little bit rounder, right? So my parabola is over here somewhere, and I'm opening up, so I'm an x squared. Somewhere 1, 2, 3, 4, 5, 6, 7, like 7, 2, 7, 3 should be my vertex, right? Approximately. So when I convert this, I should have a parabola over here somewhere, probably close by the 7, 3 vertex. So let's try this. We solve this guy for t equals in terms of x. So we subtract 7. We got to get 2t by itself. We got to solve for t, so we divide by 2. Doesn't matter how bad this looks, just leave it like this. Now, you're going to come here into the next equation, and you're going to substitute it in. You're going to take this t out, and you're going to put this t in here. This is your substitution. So we get y is equal to 2 times x minus 7 over 2, oops, I forgot 2, squared plus 2. Now, if I just graph that, I'll get a parabola. I can see my parabola, right?
Oh, so you did say we can't keep it like that, right?
You can. You can. If I want to resolve this, this is my x minus 7 squared over 4 times 2. This is coming out. So I've got x minus 7 squared. Hang on with me for 1 minute. So this almost looks like a vertex. Hang on. Let me pull out my 1/2. So it's going to be this. Isn't this my vertex form of my parabola? What's my vertex? 7, 2. Where am I opening? I'm opening up. Isn't that my 1/2, my transformation, like my dilation part of it? It says stretch it out a little bit. So it's a little bit wider than it normally would be. So this is your vertex form.
You don't have to solve.
You could leave it like this. If you want to put it in your calculator and you want to see that it's a parabola that looks like that, you can leave it like that.
That's the final answer.
You can be. Or you can get down to here, which is your vertex form.
I'd rather.
I know most of you have trouble going from here to here.
That was crazy.
Yeah, but the new part is what I'm asking you to figure out. And then if I want to, I can take my calculator, if mine was really nice and cooperative, put it back to function mode and graph this and zoom 6. And I get exactly that same parabola. Okay? Alright, so why don't you guys try number 2?